Hello, amazing people, students, lovers of chemistry out there. I'm super excited to be here with you on today's episode on this series of radioactivity that we've been looking at thus far. And in today's episode, we want to talk about the concept of radioactive decay. We want to define what it is, see some examples, and then we'll close the curtain on today's video. So now let's start off by defining what the concept of radioactive decay actually is. To do that, let's start with defining what the purpose of radioactive decay is. Now, the thing is, every atom you see in chemistry has a core, and that core is called the nucleus. Now, over here on the left bottom corner of the screen, I have the diagram of the atomic structure. All right, so you can see the atom, you can see the core or the center of the atom. This center over here is actually called the nucleus of the atom. Now, that being said, the nucleus is actually made of some subatomic particles. They are called the protons. The protons are the subatomic particles that carry a positive charge. Okay, as you can see over here, you have some balls, green colored, that are having a plus sign over them. And then we have the neutrons. The neutrons are the subatomic particles that have no charge at all. They are neither positive nor negative. And then the nucleus of an atom is usually surrounded by electrons that are orbiting around it. Electrons are actually negatively charged. That's why you can see these negative or minus signs hanging on them. So now that we have seen the subatomic particles, it is important to note that some nuclei here actually stands for the plural form of nucleus. Okay, so some nuclei are actually perfectly balanced and stable, but some other ones are not so stable. So in a case where the nucleus of an atom is not stable, something happens. Okay, now that thing that happens can be likened to the concept of a stack of blocks that we have. Now look at this stack of blocks over here. They seem very unstable. If the blocks are uneven, they begin to wobble and eventually they topple and fall down. Unstable nuclei or unstable nucleus of atoms are like that. They begin to wobble because of that instability that they have, and eventually they break down. Now, that process of breaking down is what we call the radioactive decay, and it happens so that they can become stable. So, this example we have over here, you can see this stack of blocks that is unstable falling down so that it can become more like this. This one here is a bit more stable, but this one seems a bit unstable. So when the nucleus of an atom is unstable, it begins to wobble and eventually it breaks down. That process of breaking down is called a radioactive decay. Now look at this concluding sentence here. To do this, the nucleus of an atom releases particles or energy, and that is what we call radioactive decay. So the radioactive decay is simply the process whereby an unstable atom releases energy and radioactive particles in order to become stable. So now that we have defined what radioactive decay is all about, let's go into the types of radioactive decays that we have. Now, for a start, we have three main types of radioactive decay. We have the alpha decay, and you can see the symbol denoted alpha decay. We have the beta decay, and we have the gamma decay. We're going to be looking at each and every one of them one after the other. First things first, we have the alpha decay. Okay, so during the alpha decay, what happens is that the nucleus of an atom releases an alpha particle. An alpha particle is denoted like this in radioactivity. Okay, and an alpha particle is made up of two protons and two neutrons. Now, in one of our previous videos, we talked about some important properties of an atom. We talked about the atomic number, which is denoted by a Z. We talked about the mass number, which is denoted by an A. And we talked about the symbol with which we represent elements, which is denoted by X. So now, when you denote an element using the symbol X, you put the atomic number Z at the bottom left corner over here. and you put the mass number A at the top left corner over here. So now, when we talk about the alpha particle, which is denoted like this, the alpha particle has a mass number of 4 and an atomic number of 2, which corresponds to the helium atom. The helium atom also has a mass number of 4 and an atomic number of 2. That is why in radioactivity, when we want to represent the alpha particle, we can either use this symbol or we can use this symbol. So this is the same as the helium nucleus. The helium nucleus has been shown to us over here. Now, what happens during the alpha decay? First of all, the mass number decreases by 4 and the atomic number decreases by 2. So for instance, let's say I have the uranium atom. The uranium atom has a mass number of 238 and an atomic number of 92. When the uranium atom undergoes an alpha decay, its mass number will reduce by 4 and its atomic number will reduce by 2. This is the alpha particle that has been released. So the new element that will now be formed will have a mass number of 234 and an atomic number of 92. I'm sure you're seeing how the steps are being carried out. Now, here is the example we have on the screen right now. We have uranium, which has a mass number of 238, undergoing an alpha decay, and it lost a value of 4 in its mass number and a value of 2 in its atomic number. In the process of doing that, the mass number of the new element that was formed now became 234 and its atomic number became 90. And the atomic number of the element that has the value 90 is thorium, Th. So uranium became thorium, and this gives off an alpha particle. So that's how the alpha decay is carried out. So next up, we have the beta decay. The beta decay is another type of radioactive decay whereby a neutron is converted into a proton and then an electron, which is also known as a beta particle, is released from the nucleus of the atom. So the beta particle is denoted using this symbol, and the beta particle can take two forms. We have the negative and we have the positive. The negative beta particle has these values, and then the positive beta particle has these values. The negative beta particle is called the electron, and the positive beta particle is called the positron. I'm sure you're seeing how each and every one of these steps are being carried out. So when a beta decay occurs, the first thing that happens is that the atomic number increases by 1 and the mass number stays the same. I'll take that again. The atomic number increases by 1 and the mass number stays the same. So let's see an example that treats this concept, and let's see how it comes to play as far as the beta decay is concerned. Now we have the atom of carbon 14, the radioactive atom of carbon 14. So in this case, carbon has a mass number of 14 and an atomic number of 6. It is undergoing a beta decay. Remember, during a beta decay, the mass number remains the same and the atomic number increases by 1. So 6 increasing by 1 becomes 7, and the atomic number, since it is 7, it corresponds to the element nitrogen. So the element that will be denoted here is nitrogen with a capital letter N, and then we need to add the beta particle that was radiated. So the explanation of that concept is this: carbon 14 becomes nitrogen 14 because a beta particle was emitted. I'm sure you're seeing how each and every one of these steps are being carried out. All right, now next on our list is the gamma decay. Okay, so the gamma decay is a type of radioactive decay that happens usually after the alpha and beta decay have taken place. So usually, sometimes after alpha or beta decay, the nucleus of an atom is still excited. What it means is that it still has too much energy that it cannot contain all of it. So when this happens, it begins to release this extra energy as gamma rays. Gamma rays are simply powerful electromagnetic waves, very much like super strong X rays. When this happens, the effect is that there is no change in the atomic number or the mass number, it is just simply a release of energy. This is why gamma rays are the ones that have the highest penetration power, because from A to Z they are just simply rays of energy. So now that we know that about the gamma ray, here is an example of gamma decay. Now you can see we have the element thorium, which has the mass number of 234 and the atomic number of 90, undergoing a gamma decay. Now, when the gamma decay takes place, there is no reduction in the atomic number, neither is there a reduction in the mass number. So the atom and the element remain basically the same. What happens is that it is just a radiation of energy from A to Z. So here are the explanations. The thorium atom is in an excited state. In other words, it has so much energy. That is what it means when they say an element is in an excited state. And because it has so much energy, it releases a gamma ray to help it calm down. So the gamma decay is like letting out a big sigh after you have been running. No particles are lost. It is just energy that is released. If this video is being educative for you, please like, share to as many as you can, and subscribe so we can reach as many people as possible. Now, here is a summary table of all the types of radioactive decay that we've talked about thus far. So the first one we have is the alpha decay. It has this symbol which is denoted as the helium atom with a mass number of 4 and an atomic number of 2. It can also be denoted as this, that is the alpha particle, and it has a mass number of 4 as denoted over here and an atomic number of 2. So when an alpha decay takes place, the change in mass goes down by 4. That's why you have a negative 4 over here. And the atomic number changes by -2. That's why you have a negative 2 over here. The penetration power of the alpha particle, however, is low. It can be stopped by paper. And then next up, we have the beta particle. The beta particle has this symbol E because it is an electron with a negative charge. Okay, and it has a mass change of 0. When a beta decay takes place, the mass number does not change, but the atomic number increases by 1. That's why you have a +1 denoted over here. And its penetration power is medium. It can be stopped by an aluminum foil sheet. And then we have the final one, which is the gamma radiation. The symbol is over here denoted. Can write it like this. Now, when the gamma radiation takes place, there is no change in mass, neither is there a change in the atomic number. But the penetration power of the gamma ray is the highest among all three because they are rays of energy, and it can be stopped only by lead lined boxes. All right, so now that we've talked about the three of them, here are some practice questions that I want you to carry out on your own end. We have the first question. The first question shows a radioactive element by the name polonium. Polonium has the symbol Po. It has a mass number of 210 and an atomic number of 84. Polonium is undergoing a radioactive decay, whose name I don't want to mention in this case because it's a practice question for you. And at the end of the radioactive decay, its mass number became 206 and its atomic number became 82. And then we have a new symbol or a new element formed. And then we have the particle that was released. The question now is, what type of decay is this? Go ahead, solve the question and let me know in the comment section below, where I'd be waiting to receive your answers. The next one we have is this question on the screen right now. We have carbon 13. Carbon having a mass number of 13 and an atomic number of 6, undergoing a type of radioactive decay. And then we are being asked as well, what is going on here? What type of radioactive decay is that? So go ahead, let us know in the comment section and I'll be willing to respond to each and every one of your answers. And then the third question says, after a beta decay, If the nucleus is still emitting some energy with no change in the protons or neutrons, what type of decay is that? Go ahead and let me know the answer in the comment section, and I'll be waiting to receive them. Alright, by way of summary and closing the curtains on today's video, here are some quick recaps on what we've been saying since this video commenced. First of all, why do nuclei decay? First, they decay because they want to become more stable by releasing particles or energy. And then we talked about the alpha decay. The alpha decay is simply a radioactive decay whereby the alpha particle is emitted. The atomic number reduces by 2 and the mass number reduces by 4. Then we talked about the beta decay. The beta decay is simply a radioactive decay whereby the beta particle is emitted. The atomic number increases by 1, but the mass remains unchanged. And then finally, we have the gamma decay. The gamma decay is simply a radioactive decay whereby pure energy is released because the atom is still in an excited state. It emits energy, there is no change in the mass or the atomic number. So now that we have said that, it's time to draw the curtains on today's video. I'm sure you enjoyed every bit of it, and I'm sure it was as educative as it was informative for you. All right, up next, we're going to be talking about the concept of understanding and writing nuclear equations. I'd like you to stay tuned for that episode, which will be coming up shortly. And up until then, it's bye for now. My name is David, and all I do here is to take the mystery out of chemistry so chemi can make history. I will see you in the next video.